Imagine setting off on a journey into space and returning home, only to find everyone else older than you. Or living near a black hole, where 1 hour for you equals years on Earth. It sounds like a paradox, but it's scientific reality. Over 100 years ago, Albert Einstein revealed a secret that forever changed the way we see time, space, and the universe itself. This is the theory of relativity. And what you're about to discover will make you question everything you thought you knew about reality. To understand the core idea behind Einstein's general theory of relativity, I need 2 objects, a hammer and a sheet of paper. If I asked you which would hit the ground first if I dropped them, you'd probably say the hammer. Well, in fact, that's true. On Earth it's true because there's air resistance, so the sheet of paper experiences more drag and falls more slowly. But if we could perform this experiment in a vacuum, the 2 objects would hit the ground at exactly the same time. This experiment was actually carried out by astronauts during the Apollo mission on the Moon. In the absence of air, the hammer and the feather, in that case, hit the ground simultaneously. This happens because the acceleration of falling objects in a gravitational field is independent of their mass. There's a famous experiment often mentioned, the dropping of weights from the Leaning Tower of Pisa, in which Galileo supposedly demonstrated that a lead sphere and a wooden sphere hit the ground at the same time, and thus have the same acceleration in a gravitational field. There's some doubt about whether Galileo actually performed this experiment, because with air resistance it would have been very difficult to notice that the accelerations are identical. The real fact is that the acceleration of free fall in a gravitational field doesn't depend on the mass of the objects. Einstein took this fact and built on it to form what he himself called the most brilliant idea he ever had in his entire life. And the idea was this. Imagine you are inside a closed room floating in the vacuum of space, far away from any gravitational field, far from any mass. Obviously, if inside this room you take the same hammer and the same sheet of paper and let them go, they will float because there are no gravitational fields, just drifting freely in space. But Einstein had this insight. What if the room is not far from all gravitational fields and masses, but instead is falling in a gravitational field? What would happen? Well, if the acceleration in a gravitational field is the same for all objects, then everything inside the room, you, the hammer, the sheet of paper, and the room itself, would fall with exactly the same acceleration. From your point of view, everything would look exactly the same as it did when the room was far away from any gravitational field or mass. You would see the objects floating freely, and you wouldn't feel your own weight. It sounds strange, but in fact, this is exactly how astronauts train on Earth to experience weightlessness for short periods. If you're inside a plane that's in free fall within Earth's gravitational field, everything inside falls with exactly the same acceleration, and you experience weightlessness. Not because you're far from a gravitational field, but because you're falling in one. In a certain sense, the acceleration of free fall in a gravitational field cancels out the gravitational field itself. Let's take another example. If you're inside a rocket accelerating upward, you feel an increase in weight. You feel pressed down against the rocket's floor. So the acceleration of the rocket is indistinguishable, from your perspective, from being inside a gravitational field. This was Einstein's brilliant idea. Treat accelerated reference frames as if they were inertial reference frames, but with gravity present. What comes next involves a lot of mathematics, quite complicated, but one of the most incredible consequences of Einstein's idea and the resulting general relativity can be understood fairly simply. You've probably heard that in general relativity, mass curves space. But what does that actually mean? Let's go back to the example of a reference frame far from any gravitational field, in which you turn on a laser, firing a beam of light that travels in a perfectly straight line inside your frame. Now imagine that this reference frame is no longer far from all gravitational fields, but is in free fall within one, exactly as in our earlier example. Inside this free-falling frame, as we said, You're in a situation indistinguishable from being far away from any mass or gravitational field. So for you, the light still travels in a straight line, just as it did when you were far from any gravity. But imagine looking at the situation from the outside. Your frame is in free fall, so the light moving inside it is, from an external observer's perspective, actually following a curved path, a curved trajectory. And this is where the idea of curved space comes from. In a gravitational field, light rays follow a path that is not straight, but curved. Light always travels along the shortest path between 2 points. The difference is that, in a gravitational field, space is no longer flat as it is without gravity. It's curved. So, in trying to write the laws of physics so that they would be the same for all reference frames, including accelerated ones, Einstein reached another conclusion. Gravity, which until then had been considered an attractive force between masses, could instead be described as a consequence of the curvature of space. A mass curves the surrounding space, and other objects follow the shortest paths in that curved space. This way, we can perfectly explain everything we observe, from the motion of planets around the sun to far more complex events, which we'll talk about another time. For now, we'll stop here. I hope this video has helped you understand a little better what general relativity is, why we talk about the curvature of space, and where this idea comes from. If you enjoyed this journey through the universe, subscribe to the channel so you don't miss the next adventures. We still have many mysteries to explore together. Until next time, bye!